we are now dealing with time dependent electromagnetic fields, and they satisfy all 4 Maxwell's equations. In particular, now we are going to be concerned with the wave phenomena and radiation with electromagnetic fields. So, this lecture we are going to start with wave phenomena related to electromagnetic fields E and B. So, we will motivate the wave equation for E and B, comment on that, and then start discussing wave equation in general, and then we will come back to E and B, electromagnetic waves, later. So, to start with, for EM phenomena, we always have these Maxwell's equations, and now we are going to write this for without sources. So, these fields have been created, satisfy certain boundary conditions, and in vacuum they are going to satisfy divergence of E equals 0, curl of E equals minus dB dt, divergence of B equals 0, and curl of B equals 1 over c square dE dt. These equations combine together to give you the wave equation. So, for example, if I take the curl of E equation, this gives me minus d by dt curl of B. I am now taking the liberty of exchanging the time and space derivatives as we have been doing, and the left hand side can be written as gradient of divergence of E minus Laplacian of E, which is equal to minus d by dt, and then I have curl of B equals 1 over c square d to E by dt square. Since divergence of E is 0, I get del square E minus 1 over c square d to E by dt square equals 0. I have this extra d by dt here. In 1D, this will become d 2 E by dx square minus 1 over c square d 2 E by dt square equals 0, right, where E is a function of x and t both. Similarly, if you take curl of B, which will be equal to 1 over c square d by dt curl of E, this will immediately lead to del square B minus 1 over c square d 2 B over dt square equals 0, or in 1D will become d 2 B over dx square minus 1 over c square d 2 B over dt square equals 0. So, what we get from the Maxwell's equations is that E and B satisfy this equation, del square B E minus 1 over c square d 2 B over dt square equals 0, and they lead to traveling wave solutions or stationary wave solutions, as we will see. One note of caution: every solution of the equation above is not an acceptable solution. For that to happen, the solutions have to satisfy the 4 Maxwell's equations. So, E and B have to be related in a certain way, divergence of E has to be 0, divergence of B has to be 0, all that has to happen. Just solving these two equations does not guarantee that, and this at times becomes easier when you deal with the potentials, right. So, this is a note of caution. Now, since this is a wave equation, what I am going to start with in this lecture first is discuss waves in general. So, what is a wave? A wave is nothing, but if there is a disturbance which has been given to you. So, there is suppose a disturbance which has been given to you, right. So, suppose I take a snapshot of this at time t equals 0, and this is given as a function of x, for example. As time progresses, so let us say time t greater than 0, suppose this disturbance is traveling to the right. I will not be able to reproduce this exactly, but what is going to happen is this point is going to shift. So, it is going to look something like this. It has shifted. Each point has shifted. So, for example, if I consider this point here shown by red, it has shifted to the right. If I consider this point here, it has also shifted to the right, because the wave has traveled. So, whatever the disturbance was at time t equals 0, it has shifted to the right, and the amount is going to be the shift is v times t, where t is the time taken. Suppose this function was f x at time t equal to 0. I want to find what f x is in general. So, I want to write an equation for f x t. How does this function look after time t? And this would look, because the whole thing is shifted, like a function as a function of x looked at distance f x minus v t at time t equal to 0, right, because it is shifted to the right by v t. So, if I shift it back at each x, the displacement now is what it was at x minus v t at time t equal to 0. So, that is the meaning of this. Meaning is at time t, displacement or disturbance, whatever you want to call it, it is not necessarily displacement. So, I am just going to put it in quotes. Displacement at x is what it was at x minus v t at time equal to 0. So, if I just keep shifting everything back, this time t equals 0 becomes irrelevant. So, this becomes a function of x minus v t. So, a wave traveling to the right is going to be a function of x minus v t. So, this is what we conclude from this. A wave traveling in the positive x direction with speed v is given by f x minus v t is a function of f x minus v t. So, this was a wave, and this is easier to make. At time t, it just shifted. The important thing to note is, although the wave pattern shifted, it did not change its functional form. So, these are called non-dispersive waves. For example, our sound when we speak is a good example of non-dispersive wave, because when I speak, a person who is standing far away does not hear it distorted. He or she hears it as I spoke. So, it does not get distorted that much, right. So, it is non-dispersive. Now, I will leave for you to show with the same arguments that a wave traveling in the negative x direction with speed v is described by a function f, which is a function of x plus v t. I am leaving that for you to show. So, either I have for the wave traveling to the right, I will just make an arrow, a function f x minus v t, or for the wave traveling to the left, a function, any general function x plus v t. How about the equations? So, if I call this x minus v t u, then I have partial derivative of x is equal to df du, and partial derivative of f with respect to t as df du times minus v du dt, which is partial f partial x times minus v. Similarly, for the wave traveling to the left, I have partial f partial x equals df du, if I call this x plus v t u, and partial f partial t equals df du times v now, which is equal to partial f partial x times v. And therefore, when I look at the equations for f in terms of x and t, they become as follows. So, for the wave traveling to the right, I have partial f partial x, which is df du, and partial f partial t, which is df du times minus v, which is minus v times partial f partial x, and therefore, the equation becomes df dx plus 1 over v df dt equal to 0. And for the wave traveling to the left, I will similarly show that it is df dx minus 1 over v df dt equal to 0 for wave traveling to the left. So, I have now two equations describing the waves. What if I want to have one equation and remove the distinction between left and right? So, question I am asking is, how can I have one equation removing the distinction between left moving and right moving wave, because then I will have a general thing. So, for that, what we will do is, I have df dx equals minus 1 over v df dt for the right moving wave. I will take d2f by dx square, and this will come out to be, I will operate by minus 1 over v d by dt again. So, it will become 1 over v square d2f by dt square. So, let me just write on the side what I did. I have taken the partial derivative of x to be equivalent to minus 1 over v partial derivative with respect to t. Similarly, for the wave which is moving to the left, I will have df dx equals 1 over v df dt, and again I will take now partial x to be equivalent to 1 over v d by dt. This you can show easily by the same arguments as we did earlier. and therefore, I can write this as d 2 f over d x square as 1 over v square d 2 f dt square, and both are the same. And therefore, the general equation I have is d 2 f by dx square minus 1 over v square d 2 f by dt square equals 0. That is the general wave equation. So, when I look at this equation minus 1 over v square d 2 f by dt square equals 0, it is a general equation describing a wave, and the solutions are going to be the combination of left traveling and right traveling waves. So, I can say that this is going to be a some constant a function of x plus v t plus b a function of x minus v t. This function need not be the same. I can write f 1 and f 2. So, I could have as solutions a wave which is traveling to the right, another wave which is traveling to the left, or a stationary wave. So, all three are allowed by this equation, and this is the most general wave equation. What I did so far is that I took a snapshot of a wave which was given as a function of x and then allowed it to move by v t. Let us look at it another way. So, I am going to now write another way of looking at the same thing, and that is going to be, suppose I am creating a disturbance at a certain point, right. I am creating some sort of a disturbance, and this disturbance travels as wave. And I am going to ask, at a distance x, at time t, what is the displacement? So, question I am asking is, what is the displacement f x at time t? Since the wave has traveled by a distance v t in this time, this displacement is going to be, suppose the original point is x equals 0, this displacement is going to be what the displacement was at x equals 0 at time t minus x by v, because it took that much time for it to travel, provided it is traveling undistorted. Again, I am going to make this 0 irrelevant, or whatever reference point I choose, 0, 1, 2, x naught, and the traveling wave solution is therefore going to be a function of t minus x over v, and this will be moving to the right. For that, traveling to the left, I am going to have a solution f t plus x over v. This also describes the same wave, one traveling to the left or one traveling to the right. The functional form is also the same, except that I have divided the whole argument by t and switched t and x by a minus sign. The equations, I will leave it for you to show that come out to be the same. Right. So, this is another way of looking at it. Depending on what situation you are talking about, one way or the other of looking at these waves could be more useful. So, what I want to give you now is the question is that derive the equations for wave going to the right or wave going to the left from these equations. And then also derive the general equation. Another question I want to leave for you is, if the direction of wave travel is given by unit vector n, show that the wave disturbance f is a function of n dot r minus v t or n dot r plus v t, depending on which way it is moving. Let us now show all this through an example. Example is going to be a wave, which is a transverse wave in this case, on a tight string. This you studied in your 12th grade, in your BSc, MSc, all over, but this is a nice example. So, suppose I have a string which has tension T and mass per unit length equals mu. Then this equation of motion is given by d2 y by dx square minus mu over t d2 y by d t square equal to 0, where I have taken the coordinate system such that the disturbance is given by y, the direction is x. So, what I want you to do now is consider a piece of this string of length delta x, tension on both sides is T, delta x tends to 0. So, by considering the motion of this part of the string, obtain the wave equation above. Assume dy by dx is much less than 1. So, given this equation, you can see that the string satisfies the equation d2y by dx square minus mu over t d2y by dt square equals 0. So, compare with d2y by dx square minus 1 over v square d2y by dt square equals 0, you get v equals square root of t over mu, a well known result. Now, suppose I take this string, tension T, it is in the x direction, and suppose this point is x equals 0, and at x equals 0 I start shaking it up and down, such that the displacement at x equals 0 as a function of time is given as some amplitude sine of omega t. What will be the form of the travelling wave? So, question 1 is asking what is the form of the travelling wave, and you know that y x t will be given by y x equals 0 at t minus x over v. As I said, x equals 0 is irrelevant. So, this becomes a sine omega t minus x over v. So, the displacement of this wave is going to be given as y x t equals a sine omega t minus x omega over v. Or I could have asked that this is a snapshot of the wave at time t equals 0. This is a snapshot of the wave at t equals 0. So, this looks like y x equals some sine k x with an amplitude a. Then y x at time t will be given as, and this is at time t equal to 0, y x minus v t at t equal to 0. So, this will become a sine of k x minus v t, which is nothing but a sine k x minus k v t. Both describe the same wave, and there are two different ways of looking at it. Now, let us quickly solve a problem related to whatever we have learnt. So, I am solving a problem to understand whatever we have learnt. So, I have a figure in which I have made a wave, and there are different points. This wave is traveling to the right with speed v. Here is a point A, here is a point B on this, there is point C on this, there is point D on this, and there is a point E. So, it says figure shows a photograph of a wave traveling to the right. State whether the points shown were moving up or down when a picture was taken. Which point, A or B, which one is moving faster? I can look at it physically, or I can look at the solution, right. So, I will look at the solution first, so that you get familiar with that mathematics, and then we will look at the whole picture physically also. So, in the solution, since the wave is traveling to the right, I can make use of dy by dx equals minus 1 over v dy by dt. So, dy by dx is the slope of the displacement, and dy by dt is the speed v y of speed, and this will be the vertical speed, not the wave speed, vertical v y of a point. Now, if you look at the picture, you see that dy by dx at A is negative, and therefore, dy by dt at A is going to be positive. Point A is moving up. So, A point is moving up. dy by dx at B is also negative, implies dy by dt at A is also greater than 0, B is moving up. dy by dx at C is equal to 0, it is the minimum, and therefore, the speed of point C in the vertical direction is 0, C is not moving. And same thing you can work out for D and E. If you look at the whole thing physically, what is happening is, here is this wave given moving to the right, here is point A, point B, point C, point D, and point E. A moment later, the wave is going to be as shown here. So that point A has moved up, point B has moved up, point C has remained where it is, point D has moved down. So, the speed of D is down. So, you see this is very specific to the wave moving to the right. Now, I know that the modulus of dy by dx at A is less than dy by dx at B. The slope is larger, and therefore, V y at A is going to be less than V y at B. Point B is moving faster. What I like you to do now is do the same analysis for this wave moving to the left. So, to conclude, we have seen that free fields E and B, free fields I mean source free in vacuum, satisfy the wave equation. We have discussed general form of wave equation for non-dispersive waves and solved an example. Thank you.